I'm staring at something right now that's about as exciting as a paperclip. It's a rubber O-ring, maybe an inch in diameter, sitting on my desk. Cost me about 50 cents at the hardware store. You could lose it in your pocket and never think about it again. But here's the thing that keeps me up at night. This little circle of rubber, this seemingly mundane piece of engineered material, was one of the unsung heroes of World War II. And I'm not exaggerating when I say that without it, the entire Allied war effort could have looked very, very different. We talk a lot about the tanks, the planes, the ships, the bombs. We memorialize the battles and the generals and the turning points. But wars aren't just won by the big, dramatic stuff. They're won in the machine shops, the laboratories, the tiny engineering decisions that nobody photographs for the history books. The O-ring is one of those decisions, and its story is way more interesting than you'd think. Let me take you back to the late 1930s. The world is gearing up for what everyone knows is coming, another massive conflict. And if you're paying attention to military technology, you're starting to see a problem that nobody's quite figured out how to solve elegantly. Everything is getting faster, more powerful, more complex. Aircraft engines are being pushed to unprecedented levels of performance. Hydraulic systems are becoming standard on everything from bombers to submarines. And all of these systems have one thing in common. They need seals. Now, sealing isn't glamorous, I get it, but think about what a seal does. It keeps fluids where they're supposed to be and keeps other stuff out. In an aircraft engine operating at 30,000 feet, where the temperature can swing from scorching hot to well below freezing, that's not a trivial problem. And a hydraulic system controlling a bomber's landing gear at high altitude, a leak doesn't just mean you need to top off the fluid. It means the landing gear might not deploy when you're trying to land with a plane full of bombs and a crew counting on you. Before World War II, most mechanical seals were made from leather, cork, paper, or early synthetic materials that were, let's be honest, pretty terrible at their job. They'd degrade with heat, they'd get brittle in the cold, they'd swell when exposed to different oils and fluids, and they'd wear out fast. Engineers were constantly fighting a losing battle with leaks. Military mechanics during the interwar period spent an enormous amount of time just dealing with seal failures. Enter a guy named Niels Christensen. Now, Christensen isn't a household name, and he probably never will be. He wasn't a general or a pilot or a war hero in the traditional sense. He was a Danish-American machinist and inventor working in the 1930s, and he was frustrated. He'd been tinkering with mechanical seals for years, and like everyone else, he knew the existing solutions were inadequate. In 1937, Christensen filed a patent for something he called an O-ring. The concept was beautifully simple. A ring made of rubber with a circular cross-section that would sit in a groove and create a seal when compressed. The genius wasn't just in the shape, though. It was in understanding the material science. As the O-ring was compressed, it would deform slightly, filling any microscopic gaps and creating a seal that actually got better under pressure. The more pressure you apply to the system, the tighter the seal became. It was self-sealing, self-compensating, and remarkably reliable. But here's where timing becomes everything. Christensen's patent was granted in 1939. That's the same year Germany invaded Poland and World War II kicked off in Europe. And while America wasn't in the war yet, the US military was watching what was happening in Europe very carefully and starting to ramp up production of military equipment. They needed solutions, and they needed them fast. The O-ring arrived at exactly the right moment. But it wasn't an overnight success. It took a few years for the military and manufacturers to fully appreciate what they had. Early in the war, a lot of equipment was still using old-style seals. But as aircraft got more sophisticated, as engines got more powerful, as hydraulic systems became more critical, engineers started discovering that this simple rubber ring could solve problems they'd been fighting for decades. Let me give you a concrete example that really drives home how important this was. The Boeing B-29 Super Fortress, one of the most advanced bombers of the war and the plane that would eventually drop the atomic bombs on Japan, was a maintenance nightmare early in its development. It had pressurized cabins, remote-controlled gun turrets, and incredibly powerful engines. All of this required hydraulic systems and pneumatic systems that were far more complex than anything that had come before. The early B-29s were plagued with leaks, hydraulic fluid leaking everywhere, pressurization systems failing, gun turrets that wouldn't operate properly. Engineers working on the B-29 program started replacing traditional seals with O-rings, and the difference was night and day. Leak rates dropped dramatically, system reliability improved, maintenance hours per flight hour decreased significantly. Now, I can't find the specific document that says O-rings saved the B-29 program, but the timing and the technical reports from that era tell a pretty clear story. By late 1944, O-rings were becoming standard in American military aircraft, and the B-29s that were flying combat missions over Japan were far more reliable than the early prototypes had been. But it goes way beyond just bombers. Think about the P-51 Mustang, arguably the best fighter plane of the war. The P-51 had a liquid-cooled engine, which meant it had a complex cooling system with multiple points where coolant could leak. Early P-51s had some issues with coolant leaks that could lead to engine overheating and failures. As O-rings were introduced into the cooling system connections and various engine components, reliability improved. Pilots flying deep into Germany on bomber escort missions needed to know their engines wouldn't quit on them 500 miles behind enemy lines. O-rings helped make that possible. And it wasn't just aircraft. Naval vessels were using O-rings in everything from submarine periscopes to torpedo tubes. The German U-boat threat in the Atlantic was one of the most serious challenges the Allies faced. And submarines are basically floating, sealed environments where any leak is a potential disaster. American submarines started using O-rings in critical systems, and the reliability improvements were significant. A submarine that has to surface prematurely because of a hydraulic leak is a submarine that's vulnerable to attack and can't complete its mission. Here's something that really gets me. The Manhattan Project, the top-secret program to develop the atomic bomb, relied heavily on O-rings. The gaseous diffusion process used to enrich uranium required massive facilities with thousands upon thousands of seals. Any leak in these systems wasn't just an inconvenience, it was a security risk and could contaminate the entire process. O-rings were used extensively in the Manhattan Project facilities, and their reliability was crucial to keeping the program on schedule. Without reliable seals, the atomic bomb program would have taken longer, cost more, and might not have been ready before the end of the war. Let me throw some numbers at you to give you a sense of scale. By 1945, American manufacturers were producing millions of O-rings per month for military applications. Millions. The Parker-Hannifin Corporation, which became one of the major O-ring manufacturers, saw its production increase by over 500% between 1941 and 1945. These weren't expensive, complicated parts. They were simple, cheap, and mass-producible. But their impact was everywhere. Now, I need to be careful here because I don't want to overstate the case. O-rings didn't win World War II by themselves. Wars are incredibly complex, and there's never one single factor that determines the outcome. But what O-rings did was solve 1,000 small problems that, collectively, added up to a significant advantage. Every hour a mechanic didn't have to spend fixing a leak was an hour they could spend on other maintenance. Every plane that didn't have to abort a mission because of a hydraulic failure was a plane that could complete its objective. Every submarine that didn't have to surface prematurely because of a seal failure was a submarine that could continue hunting enemy ships. There's something else worth mentioning here: the German perspective. German engineers were aware of O-ring technology, but they never adopted it on the same scale as the Americans. There are a few reasons for this. First, Germany had limited access to synthetic rubber compounds that worked best for O-rings. The Allied blockade cut off Germany's access to natural rubber from Southeast Asia, and while they developed synthetic rubber programs, the materials they produced weren't always ideal for O-ring applications. Second, German manufacturing was more fragmented than American manufacturing, and standardization was harder to achieve. The Germans were brilliant engineers, but their production methods were often less efficient than the American mass production approach. This meant that German aircraft and vehicles often had more maintenance issues related to seals and leaks than their American counterparts. It's one of those small advantages that doesn't show up in dramatic battle footage, but matters a lot when you're trying to keep a large military force operational over several years of intense combat. I want to talk about the material science for a minute because it's actually fascinating. The O-rings used in World War II weren't made from natural rubber. They were made from synthetic rubber compounds, specifically a material called Buna-N or nitrile rubber. This material was developed in the 1930s and had properties that made it ideal for O-rings. It was resistant to petroleum-based oils and fuels, it maintained flexibility across a wide temperature range, and it didn't degrade quickly under pressure and compression. The development of nitrile rubber was itself a response to geopolitical concerns. The United States and other allied nations knew that if war broke out, they'd lose access to natural rubber from Southeast Asia, and they were right. By 1942, Japan controlled most of the world's natural rubber supply. The synthetic rubber program became a national priority, and nitrile rubber for O-rings was one of the success stories. By 1944, the U.S. was producing over 800,000 tons of synthetic rubber annually, and a significant portion of that was going into O-rings and other sealing applications. There's also a security angle to this story that doesn't get talked about much. O-rings were used in encryption machines and other sensitive equipment. The famous Enigma cipher machines that the Allies worked so hard to break, they had mechanical seals in some of their components. When Allied forces captured German equipment, they sometimes found that seals were a weak point. They degrade over time, allowing moisture into sensitive electronics and causing failures. The O-ring technology that Allied forces were using in their own equipment was more reliable, which meant that Allied encryption machines and radio equipment tended to be more robust in field conditions. Fast forward to the end of the war, and O-rings have become so ubiquitous in military applications that they're basically invisible. Nobody's writing newspaper articles about them. Soldiers and pilots and sailors are using equipment with hundreds of O-rings in it and never thinking about what would happen if those seals failed, which is exactly how it should be. The best technology is the technology you don't have to think about. But here's where the story gets even more interesting. After World War II, O-ring technology exploded into civilian applications. Suddenly, all the mass production capacity and expertise that had been developed for military purposes was available for commercial use. O-rings started appearing in automobiles, in home appliances, in industrial equipment, in plumbing systems. The post-war economic boom was built partly on technologies that had been refined during the war, and O-rings were definitely one of those technologies. By the 1950s and 1960s, O-rings were absolutely everywhere. They were in refrigerators, air conditioners, hydraulic systems on farm equipment, you name it. The automotive industry in particular embraced O-ring technology. Modern car engines have dozens of O-rings in them, sealing everything from fuel injectors to oil passages to cooling system components. The reliability of modern vehicles owes a lot to the humble O-ring. And then there's the space program. In the 1960s, as NASA was racing to put a man on the moon, O-rings were being used in rockets, spacecraft, and ground support equipment. The Apollo program relied heavily on O-ring technology. The lunar module that landed on the moon? Hundreds of O-rings. The life support systems that kept astronauts alive? O-rings. The hydraulic systems that control the Saturn V rocket's massive engines? You guessed it, O-rings. Unfortunately, O-rings also have a tragic place in space history. In 1986, the Space Shuttle Challenger exploded 73 seconds after launch, killing all 7 crew members. The cause? An O-ring failure in one of the solid rocket boosters. The O-ring had become brittle in cold temperatures the night before launch, and it failed to seal properly. Hot gases escaped through the gap, leading to the catastrophic failure of the booster and the destruction of the shuttle. The Challenger disaster was a reminder that even simple, well-understood technology can fail if it's used outside its design parameters, or if the warning signs are ignored. The O-rings in the Challenger's boosters were basically the same technology that had been used successfully for decades, but they were operating in conditions they weren't designed for. The investigation that followed led to improvements in O-ring materials and design, and to better protocols for evaluating weather conditions before launches. But let's come back to World War II, because that's where the story really matters for our purposes. The O-ring is a perfect example of what I call invisible infrastructure technology. These are the technologies that nobody notices, that don't get mentioned in history books, but that make everything else possible. The Sherman tank gets all the glory, but it doesn't run without reliable seals in its engine and transmission. The B-17 bomber is legendary, but it doesn't complete its mission if hydraulic leaks ground it before takeoff. I think about this a lot when I'm reading military history. We focus on the dramatic moments, D-Day, the Battle of Midway, the Siege of Stalingrad. But behind all of those moments are millions of small technical decisions and innovations that made those operations possible. The O-ring is one of those innovations. It's not glamorous, nobody's gonna make a movie about it, but it was absolutely essential. There's also a lesson here about the importance of seemingly mundane engineering work. Niels Christensen, the guy who patented the O-ring, wasn't trying to change the world. He was just trying to solve a practical problem with mechanical seals. But his solution ended up being used in millions of applications and probably saved countless lives by making military equipment more reliable. How many planes didn't crash because a critical seal held? How many submarines didn't sink because their systems remained watertight? How many lives were saved because equipment worked the way it was supposed to? We'll never know the exact numbers, but I'm confident they're significant. I also think about the contrast between complexity and simplicity. The trend in technology is always toward more complexity, more features, more capabilities, more sophistication. But sometimes the best solution is the simplest one. The O-ring is just a circular piece of rubber sitting in a groove. That's it. No moving parts, no complicated mechanisms, no electronics. Just material science and geometry working together to create a reliable seal. There's elegance in that simplicity. When I hold that 50-cent O-ring in my hand, I'm holding a piece of technology that helped win World War II, put a man on the moon, and makes the modern world function. It's in the engine of your car, the faucet in your kitchen, the hydraulic brakes on your bicycle, the air conditioning system in your house. It's everywhere, doing its job invisibly and reliably. The story of the O-ring is also a story about the American industrial machine during World War II. The ability to identify a good solution, scale it up to mass production, standardize it across thousands of different applications, and distribute it to every corner of the military. That was the American advantage. The Germans had brilliant engineers and innovative designs, but they couldn't match the sheer productive capacity and organizational efficiency of American industry. The O-ring is a perfect symbol of that. A simple technology, mass-produced by the millions, making everything work just a little bit better. There's one more thing I want to mention. In researching this story, I came across multiple references to the O-ring standard that was established during World War II. The military needed O-rings in hundreds of different sizes for different applications, and they needed those O-rings to be interchangeable. You couldn't have every manufacturer making slightly different sizes and expecting them all to work properly. So they established standard sizes and specifications. Those standards, developed under wartime pressure, became the industry standards that are still used today. When you go to a hardware store and buy an O-ring, the sizing system you're using was established in the 1940s for military applications. That kind of standardization is another invisible but crucial contribution to modern technology. It means that parts from different manufacturers are compatible with each other. It means that a mechanic in California can order a replacement part and know it will fit the same as the original part, even if it came from a different supplier. It means that designs can be shared and replicated without having to reinvent everything from scratch. The military's push for standardization during World War II had ripple effects that continue to benefit us today. So where does this leave us? What's the takeaway from the story of the O-ring in World War II? For me, it's a reminder to pay attention to the invisible stuff. History tends to focus on the big, dramatic events and the famous personalities, but wars are won and lost on logistics, on reliability, on the accumulation of small advantages. The O-ring gave the Allies a small advantage in equipment reliability. Multiply that small advantage by millions of applications across the entire military, and it adds up to something significant. It's also a reminder that innovation doesn't always look innovative. The O-ring wasn't a radical breakthrough. It was an incremental improvement on existing seal technology. But incremental improvements, widely applied, can have enormous impact. Sometimes the best innovation is just doing something simple really well. And finally, it's a story about the interconnectedness of technology and history. The synthetic rubber program that made O-rings possible was driven by geopolitical concerns about access to natural rubber. The mass production techniques that made millions of O-rings available were developed in response to wartime needs. The standardization that made O-rings interchangeable was driven by military logistics requirements. And all of that fed back into civilian applications after the war, contributing to the post-war economic boom and eventually enabling the space program. The next time you change the oil in your car and see those little rubber O-rings on the drain plug and oil filter, or when you replace a faucet washer in your kitchen, take a second to appreciate what you're looking at. You're looking at a technology that helped win World War II, that keeps submarines from sinking and planes from falling out of the sky, that makes the modern world work. It's not exciting or glamorous, but it's important, and that's knowledge you now have. The O-ring, proof that sometimes the smallest parts play the biggest roles, and that the most important innovations are the ones we never think about because they just work. That's the kind of engineering I can get behind.